The Renninger negative result experiment is not a physical experiment that was performed, but a famous thought experiment in quantum mechanics. It was proposed by Mauritius Renninger in the 1950s to highlight a paradoxical aspect of the standard interpretation of quantum measurement, particularly the concept of wave function collapse. The paradox, the core idea of the Renninger experiment, is that a measurement can occur even when there is no physical interaction between a particle and a detector. The lack of a positive detection can be just as informative as a positive one. Here's the general setup. 1. A source emits a particle, like an alpha particle from a radioactive atom. 2. A set of detectors are placed in a spherical shell around the source. 3. One of these detectors is special. It's a local detector, and if the particle is detected there, the experiment is over. The paradox arises when the local detector does not register a particle. According to classical physics, this is a non-event. But according to quantum mechanics, it's a profound measurement. The negative result, positive result. If the local detector registers the particle, the wave function is said to have collapsed to a state where the particle is at that location. This is the expected outcome of a quantum measurement. Negative result. If the local detector doesn't register the particle after a certain time, we now know for sure that the particle is not in that location. Since the wave function describes the probability of finding the particle everywhere, the non-detection at that one spot means the wave function must have changed. It must have collapsed to a state where the probability of finding the particle at the location of the detector is 0. The key point is that this collapse happens without any physical interaction between the particle and the detector. The information gained from the lack of a result, the negative result, is enough to cause a change in the quantum state. Why is this significant? The Renninger negative result experiment is a thought-provoking challenge to our understanding of quantum measurement. It raises difficult questions. What is a measurement? Is it an interaction, or is it simply the acquisition of knowledge? What is wave function collapse? Is it a real physical process that happens instantaneously, or is it just an update of our knowledge about the system? Is the wave function a real physical entity, or just a mathematical tool? The fact that non-measurement can cause it to change suggests it might be more than just a tool. The experiment is often discussed alongside other famous quantum paradoxes, like the Elitzur-Weidmann bomb testing problem and Hardy's paradox, all of which explore the bizarre consequences of measurement in quantum mechanics. While it's a thought experiment, modern technologies have led to real-world experiments that demonstrate similar principles, known as interaction-free measurements.